Alrighty, welcome back to Fun Maths. Today we're looking at rates of change as part of our applications to differentiation and anti-differentiation. So again, we've looked at this in the past, but we're just sort of going to look at how we can apply this in action. So a reminder of the two different sort of rates of change that you can be asked about. You could be asked about the average rate of change. And again, if you are asked about the average rate of change between A and B, or two points, it's given as f of B take away f of A divided by B take away A. So essentially you're just finding the gradient between these 2 points. And the instantaneous rate of change is essentially where you are finding the derivative at a particular point. Again, if you work out the derivative and it's greater than 0, so a positive value, it's going to have a positive gradient, which means as there's an increase in the value of y, there is an increase in the value of y when you increase the value of x. And likewise, if you work out the derivative and it's less than 0, so a negative value, it's a negative gradient, then it's going to represent a decrease in the y value as we increase the x value. Alrighty, here is a first example that we're going to be looking at. It says here, for the function with the rule f of x equals x squared plus 2x, first of all it's asking us to find the average rate of change between 2 and 3. So again, we write out the rule for average rate of change. First of all, we're going to find out the value f of 3. Then we're going to subtract the value of f of 2 from this function. So it's a matter of substituting 3 into this function to get that, substituting in 2 into the function to get that value. And then we're going to divide that by, obviously, the b value, take away the a value. Running that calculation, we get the average rate of change there between 2 and 3 is 7. Perfect. Again, they can ask you to work out the average rate of change for this interval, with the a value being 2 and the b value being 2 plus h. Again, you still do the same thing. Again, you need to find out f of b, so substituting that into the equation, taking away f of 2, substituting that into the equation, again dividing by the b value, take away the a value. It's a matter of running that calculation, expanding things out, again grouping like terms, and then simplifying things down. In this particular case, we get the average rate of change is 6 plus h. Next one, it says the instantaneous rate of change of f with respect to x when x equals 2. So what we need to do is find the derivative of f. So finding f dash x, we are differentiating this here, we get 2x plus 2. We want to find out what's happening when x is equal to 2 at that particular point. So what we need to do is substitute x equals 2 into the derivative. So f dash 2, and we can work out that that is equal to 6. Perfect. Next example. Oh, cool, it's a balloon example. It says here, a balloon develops a microscopic leak and gradually decreases in volume. Its volume, which is represented with V, at time t, and that's in seconds, is this equation here. Obviously, time is going to be greater than 0. We're not going to negative time. Alrighty, first thing it says is find the rate of change of the volume after 10 seconds and then also after 20 seconds. So what we need to do to run this calculation and to work this out is, first of all, we need to work out what the derivative is of this particular function here. So we've got the equation for the volume here. We can work out the derivative, which is dv dt, and we can calculate that. We get negative 10 take away t over 50. Perfect, we've got the derivative. Now, what we need to do is find out what's happening, what the rate of change is after 10 seconds. So what we're going to be doing is we're going to be substituting time as being 10 into the derivative. So when t equals 10, we're going to plug that into the derivative here. 10 over 50 simplifies down to 1 over 5. We can run that calculation. It's negative 10 and 1/5. Now, again, what that actually means is that the volume is decreasing because it's a negative value at a rate of 10 and 1/5 um, centimeter cubed per second. Yep. So that's the volume. It's decreasing per second. Again, we can do the same thing with time equals 20, substituting that into the derivative, and we get negative 10 and 2/5. Again, it's still a negative value. It's decreasing at a rate of 10 and 2/5 centimeters cubed per second. Alrighty, next one. It says, for how long could the model be valid? Alrighty, so what we need to know with this particular thing is that the model will be not meaningful when v is less than 0. Yep. So we're only looking at things when it's greater than 0. Let's make v equal to 0. So here is the equation for the volume. We're making it equal to 0. We need to solve that to find out what t is when v equals 0. Now, for this particular case, probably the easiest way to do this is to use the quadratic formula. Again, this here, the coefficient in front of the squared term is going to be the a value. In front of just the coefficient of t is just going to be the b value, and this is going to be the c value. So plugging it into the quadratic formula as follows, you can get some solutions. Obviously we've got a negative 1056.78, and you've also got the other solution, or the second solution is 56.78. Again, because only meaningful values are going to be where the volume is greater than 0. We're not looking at negative volumes and negative times. What we are expecting is the solution here is t being equal to 56.78. Alrighty, now again, what we can do is we can do the same sort of thing on the calculator. So let's check out how you could do this type of thing on the calculator. So you can go to the main section here. What I would do then is you can define that particular function. So if we type this in here, make sure all variables are cleared. Clear everything so there's no dramas. So let's type in this equation. V is equal to 600, take away 10t, take away, I'm doing 1/100th in brackets, so 1 divided by 100, t to the power of 2, so up hat 2. Now, what you do to define it, you select the information, you can go to interactive and you can go to define. So it saves you typing it into this section by highlighting it. Here you need to actually put in what the function name is going to be. In this particular case, it's v. And the variable, we're dealing with time, so t here. So change this to a t. We press OK. Cool. Now, what I should have perhaps articulated there is you do not need to put in that v equals. Sorry, you just need to have the actual equation. So let's get rid of that. It's defined. Perfect. So again, let me just demonstrate that so I don't make that mistake again. It's not v equals, just do 600, take away 10t, take away 1 over 100, t squared. Yeah, sorry, when you go to define it, yeah, it doesn't have in the expression v equals. You're actually putting it up here in the function name v and t there. When you click OK, what happens is it will define it as follows. Perfect. Alrighty, the next thing we can do is we can actually differentiate the volume equation. So if you again had this here, v t, if you highlight that, remember this is the function, if you want to differentiate that, I'm just going to go to interactive after highlighting it. I'm going to go to calculation and I'm going to go to diff. Again, here's what we want to differentiate, which is the function which we've defined. The variable is t, just leave order as 1. We click OK, and it will give us the derivative. Again, you can click on standard, click on that again and press execute, and it will give it to us in the standard format. Perfect. So we could get the derivative that way on our calculator. Next thing you could be asked to do is obviously find out what's happening when t was equal to 10. So again, you can use this derivative. So I'm just going to copy it and paste it here. Now what we can do, we can tell it to substitute in 10 or t being equal to 10. Now to do this, you need to use what's called the bar symbol. Now it's on the keyboard in Math 3. It's this one here, little bar symbol. Cool, so we've got the bar. And from there, we're going to say make 10 equal to, or t equal to 10, sorry. So after the bar, you put what you want t to be equal to, or press execute, and you get negative, obviously 51 over 5, which is this here. Again, we can do the same thing. Oops, copying, selecting it, copying it, paste. So I'm changing it, t being 20. Cool, we can run that there pretty straightforward. Next thing we can do is find that meaningful situation. So again, you could go as follows. You could go, we want VT, VT to be greater than 0. And so essentially, rather than doing the quadratic formula and things like that, we can get the calculator to solve it for us. So we want to find out where VT is greater than 0. Highlight it, we go to interactive, and we go to equation, and we're going to go to solve. Here's the equation we want to solve where it's greater than 0. Remember the change of variable, it was t. Cool, it spits out where where VT was greater than 0. Now again, we can change that into decimal, which might make more sense. And we'll run that again, execute. And you can see that t has to be greater than a negative 1056, but less than 56.77. So again, because we're dealing, we're looking for the most suitable thing. Obviously, it's supposed to be between 0 and 56 here. So that's how you do it on the calculator. Thank you very much for listening. Bye for now.